Hi everyone, I'm Dragos, and today I'm going to talk to you about bf4, our tool to ensure bug-free P4 programs. P4 has recently emerged as the standard programming language for programmable network data planes. And while P4 programs are generally simpler and safer than their C counterparts, they still exhibit bugs, undefined behaviors, which may, at their turn, trigger more severe consequences. So clearly, ensuring bug-free P4 programs is an important problem. Here's a simple P4 pipeline. It consists of a set of programmable blocks which are chained together. It all starts with the parser. The packet, as a bit string, enters the parser and gets converted into a discrete set of packet header fields. They are passed on to the control block, which does classification and packet mangling. The modified header fields are then passed on to the deparser, which recombines them into a packet as a bit string, which is then sent out on the wire. Now, the main programmable parts of a P4 program are table entries. They are essentially the interface between the P4 world and the outside world. They dictate essentially the flow of the program as a whole. It is the job of a different piece of software external to the P4 world to populate table entries. This is the P4 controller. Now, unfortunately, P4 programs may exhibit bugs. Let me show you what I mean by that. Let's zoom into table NAT. I'll use this as our running example from now on. Table NAT performs source address translation. It takes as input the IPv4 source address and translates it into a new address by means of action do NAT. What happens if we call action do NAT, but there is no IPv4 header there? Well, the standard clearly mandates that this is an undefined behavior. But just to give you an idea of how bad this may get, our exploration shows that on some targets, this may actually lead to overwriting valid header fields with the value prescribed by the controller. So what we want to achieve is bug-free P4 programs. What do we mean by bug-free? Well, first of all, we'd like to have no undefined behaviors. This means no invalid header accesses, no array indices out of bounds, no egress spec related bugs such as not setting the egress spec by the end of the ingress pipeline. So far, verification tools do a great job in actually finding bugs. There are essentially two main approaches to P4 verification. One of them, taken by P4V and assert P4, assumes all table entries are actually possible. Well, not all table entries are actually possible, so this may lead to many false positives. It is then the job of the programmer to write code annotations in order to rule out infeasible table entries. The second approach, taken by Vera and P4 Node, assumes that the programmer provides the verification engine with a set of table entries. The verification engine will then check correctness of the program only in the context of these table entries. Intrinsically, this approach is incomplete in that it provides no global correctness guarantees. bf4 works along the same lines as P4V and assert P4. Now, the main caveat of this approach is that, well, writing annotation is really hard, especially writing them at compile time when the controller may not even be known. So this brings us closer to our main research question. Can we achieve bug-free P4 programs without having the user write many annotations or provide an exhaustive set of table entries. These are the key ingredients to ensure bug-free P4 programs. I'll dive into each one of them, but for now, it is important to understand what are the high-level steps taken by verification tools and also by bf4. First of all, the program is instrumented. In our running example, we add this if statement before the possibly buggy instruction. Now, this if statement reads, if there is no IPv4 header, then transition to a buggy state and end the execution. Then the instrumented program is converted into a control flow graph, which is then optimized by using some standard compiler optimization techniques. And then we generate a verification condition. A verification condition is a formula which describes all inputs which trigger buggy runs. We then feed this formula into an SMT solver, such as Z3, which then outputs SAT if there is indeed a run which is buggy, and unsat if the program is actually correct. Let's take a closer look at table NAT. Assume these table entries. Now, the rule in green works fine, because it can never trigger an undefined behavior. On the other hand, the red rule is buggy. Not only that, but for all packets which match this rule, they will end up in a buggy state. Here's how to handle this situation. We instruct the controller to never populate this kind of entry, and at the same time we generate an annotation to filter out this situation. If the bug was previously reachable and due to the added annotations it now becomes unreachable, we say that the bug is controlled. Here's a key observation. In practice, we notice that a large part of the reachable bugs are actually controlled. Okay, so this is great. How about the remaining uncontrolled bugs? Let me show you an example. Table IPv4 LPM from our sample pipeline does longest prefix match against the IPv4 destination address. It may then forward the packet down a given port using action do forward. Action do forward also does time to leave decrementation. If the IPv4 header field is invalid, then we end up in an undefined behavior state similar to the one encountered earlier in the case of table NAT. Let's take as example the rule, this table entry. There are essentially packets which match this table entry and will trigger the undefined behavior, and some of them which don't. It would be great if we could distinguish between these two cases. What's missing to rule out this non-determinism? Well, actually, it's the validity bit of the IPv4 header. What if we add the validity bit of the IPv4 header to the set of table keys of table IPv4 LPM? Well, this is what the table entries look like. Clearly, the rule in green will never trigger bugs. The rule in red, however, will always trigger an undefined behavior, and thus can be filtered out by the controller. This means that this bug has now become controlled. So here's the idea. Whenever we are dealing with an uncontrolled bug, we can convert it into a controlled bug by simply adding extra table keys. Now that I've shown you the high-level idea behind bf4, I'll now switch to showing you how to compute fixes and inferring specs to rule out buggy runs. Recall that verification tools consist of these steps. bf4 is no different, with one notable exception. Instead of computing just one verification condition, we compute two of them. Bug, which describes inputs which end up in buggy states, and OK, which describes inputs which end up in well-defined forwarding states, such as forward or drop. Now, the problem we are trying to solve is find filters which preclude as many buggy runs as possible, but don't inhibit any good runs through the program. Why is this needed? Well, if the program with the filters attached has the same good runs as the previous one, it means that whatever the user was able to express in the previous program, he would also be able to express it in the second program. Okay, now let me show you how this thing works. The algorithm starts with OK and bug. The formula is computed by bf4. It then uses an SMT solver, in our case Z3, to check satisfiability of bug. If it is satisfiable, we get a model. The model contains all packet and table entry variables. Since we only care about table entry variables, we project away the packet variables and end up with a larger formula. We then check to see if this formula intersects the OK one. If it doesn't, then we could just keep this as a spec. But since we want to ensure as many buggy runs are trimmed away, we try to compute a larger set using the solver's unsat core capabilities. We now end up with P1, which reads, whenever a table entry matches P1, it will definitely lead to a bug and should be avoided. We continue the process and we get a new model, project, and then compute the unsat core. And again, we get a model, project, and this time we notice that there is indeed an intersection. So this is the non-deterministic case I was talking about earlier, whereby for the same table entries, there is a packet which triggers a bug, and one of them which ends up in a well-defined state. So how do we rule out this non-determinism? Well, we add the extra keys until the projection and the OK set no longer intersect. Then we go on and compute unsat core and end up with P3. So the outputs of this algorithm are the inferred keys plus P1, P2, and P3, which are the specs that ensure there are no buggy runs in the program. They read as follows. If an entry matches either P1 or P2 or P3, then this entry is essentially a bug. Otherwise, you can insert it and it's fine. Okay, other than what I've shown you so far, bf4 also has some extra features and optimizations. I'm not going to go into the details, you can find them in the paper. I'm just going to focus on one of them. So clearly the algorithm I've shown you before works, however it doesn't scale very well. In order to solve this problem, we came up with this heuristic algorithm which works in most cases. Let me show you how it works. So here's the control flow graph of table NAT in our running example. Clearly, you can see that it may exhibit a buggy run. Let's take a path from table application to the bug. What are the variables which influence the control flow going down that path? Well, first of all, there is the chosen action. Secondly, there is the IPv4 validity bit. But notice that both of them are arguments of the table application. So this means that the path condition to reach the bug from this particular table call is controlled by the table. Okay, so this means that there is indeed a spec which controls this bug, and this spec is whenever an entry has action do not, then always ensure it matches only IPv4 packets. Okay, so now that I've shown you the static part of bf4, I'll now focus on how to ensure the correctness properties inferred by bf4 are respected at runtime. So in order to do that, what we do is that we insert a shim software between the controller and the P4 data plane, which intercepts all table modifications. It then checks to see whether the specs inferred by bf4 work against the resulting table entries. If they match, then the change is allowed to go through. Otherwise, an exception is thrown and the controller must handle it. What makes it work is the fact that the specs inferred by bf4 are small enough to be efficiently checked at runtime. Okay, now that we have all the pieces together, let me now show you how bf4 works against some example P4 programs. First of all, bf4 is implemented as a P4C compiler backend with full support for V1 model and partial support for TNA and PSA architectures. I'll just brief you on the numbers obtained for switch.p4, our largest example. Without any specs inferred, there are 155 bugs. When just inferring specs without any fixes, we end up with 55 bugs. And after having inferred the 23 missing fixes, then the program ends up with 0 reachable bugs. All these steps, so basically computing the specs, computing the fixes, and checking correctness of the verification condition, is performed in roughly 4 minutes. I'm now going to wrap up my presentation. I've shown you bf4, our tool to ensure bug-free P4 programs. To make sure that the process stays fully automated, we employ a mix of data plane, code fixes, static verification, and runtime checking to ensure bug-free P4 programs. bf4 is open source. You can download it here. I'm now going to switch to showing you how to run bf4 against a simple program. I'll run bf4 against the running example in my presentation. Let me remind you of what it looks like. The ingress control has tables NAT and IPv4 LPM. Table NAT takes as input the source address and may call action doNAT to map it to a new address. Table IPv4 LPM does longest prefix match against destination IP and may forward the packet on a given port using action doForward. Action doForward also does time to live decrementation. Okay, first step before running bf4, we instrument and pre-process the initial program for verification. Here's how. Now, we run bf4 against the instrumented program. I summarize the output to show only the number of bugs reachable. Now let me show you what the specs look like. They are parsed by our shim. As you can see, there are 2 uncontrolled bugs. Here are the inferred fixes. We're missing key IPv4 is valid in table IPv4 LPM. Let's add it. Again, we pre-process the program and rerun bf4. Notice that now there are no more uncontrolled bugs remaining. Thank you for your attention. I'm looking forward for your questions.